Okay, welcome to lab here. So as I mentioned before, this is really the last week here. So we got one more day after this on Thursday. So just to make sure we kind of can finish all the material we should cover here, we're going to lecture here during lab time and finish up hopefully 21. And like I said, that will leave us really just organic, which we're just going to kind of do a survey of organic chemistry. And we'll lecture on that obviously on Thursday, which is chapter 20, I believe. And then I think there's like a organic lab that goes with that. And we'll do that on Thursday. And then, if I'm not mistaken, we then have, I believe, lab final on Tuesday and lecture final on Thursday, and we'll talk more about that on this coming Thursday as well, just to make sure everybody's on the same page in terms of time and when all that is. Um, okay, so like I said, we'll be finishing up here hopefully 21, and we'll call it a day probably after that. So we've been talking about nuclear chemistry. So as we talked about earlier today, again, nuclear chemistry, a little bit different in terms of sort of the reactions and how they develop than our sort of traditional chemical reactions. Again, the major difference, as we talked about earlier today, was the idea that we really don't have that conservation of elements like we do in a chemical reaction. And again, that is because of what actually sort of changes in these type of reactions. So it's really the nucleus or those nucleons, the protons, the neutrons, as we talked about earlier today. Again, some of them we may convert, say, a proton to a neutron or a neutron to a proton. And again, because we're really changing those subatomic particles in the nucleus, as we talked about, we do end up usually producing new elements, if you will, or nucleuses. In addition, there's usually a pretty good energy sort of given off a lot of times in these processes because really, if you think about it, you into that nucleus, it's very hard to sort of change those sort of guys. And it does require a pretty big sort of change in energy. And that's again, as we'll see here shortly, and as we talked a little bit about earlier, there's usually a pretty big difference in terms of energy that's produced as a result of a nuclear reaction and energy that's as a result of, say, a chemical reaction. Nuclear reaction typically gives off a lot more energy than a exothermic chemical reaction. We talked about balancing these nuclear reactions or equations, and they're not super hard to balance. Basically, there's two things you got to make sure of. All the mass numbers on the left hand side of the arrow pretty much adds up to the exact same number on the right hand side. And same thing with our atomic number. All of the atomic numbers on the left hand side adds up to the atomic numbers on the right hand side. As we saw, we can use sort of the atomic number to our advantage because that tells us sort of what element we're dealing with. And we can kind of work our way backwards to figure out the missing mass number as well. We finished up talking about sort of stability. One very big way that we could kind of calculate stability is the N to Z ratio, and that's basically neutrons to protons. And depending on sort of the atomic number of the nucleus as to what an acceptable sort of stable ratio is, and if it's too high or too low, it will go through a decay process to try to get itself, again, not always 100% back onto the value of stability or belt of stability, but again, move itself in sort of the right direction, whichever way that may be, either too high or too low, to get itself back into a more sort of stable situation. So we saw one example where just one decay process moved us to like perfectly sort of stable. We saw another one where it didn't really give us that perfect ratio, but it definitely did move us in sort of the right direction. Um, we finished up sort of talking about just a minute ago about decay series. And again, that's just a series of decay reactions that occur. And again, one right after the other. And again, it will continue in a process until something that's very stable is basically hidden. And then it will sort of stop. So there was two ways that you could sort of do that. You could do it just kind of the old school way, if you will, and just sort of write out each nuclear equation individually. Again, taking the product from the first one becomes a reactant in the second one, and until you get to where you want. If you're not necessarily interested in each individual step per se, and just want to know what is sort of the end result of this decay series, you could kind of do it mathematically if it involves alpha and beta decays by subtracting 4 for every alpha decay from the mass number, 2 for every alpha decay from the atomic number, and adding back 1 for every beta decay that you have to the atomic number. So we did uranium 238. I just made up a little decay series, but here's kind of really the official sort of decay series. And it actually goes through 2 separate routes, if you will. It sort of starts here, and then it will sort of either go kind of to the right or to the left in that sort of pattern. And as you can see here, it sort of separates somewhere around here, and it will go one way or the other. But ultimately, they both get down to sort of a version of lead there, which is a stable nucleus, and it will continue to sort of decay until it reaches that. There can be other combinations as well that occur. But again, this is sort of our decay series. Could be very short, could be very long until it hits something that is relatively stable. Any questions on that there? The next thing we're going to talk about then is kinetics and radioactive decay. So the good news is it is kinetics, and the even better news is it is the same kinetics that we've talked about before. So when we did our kinetics chapter, it really is the same stuff here that we see in this chapter. And all radioactive decay basically follows first order kinetics. So if you remember our first order kinetics rate laws, we had the natural log of A equals the natural log of A naught minus KT. We also had a half-life, which is very important kind of in this one. It's the natural log of 2 divided by K. That's that 0.693 number divided by K. So these equations here that we saw earlier are really the same equations that we use here in radioactive decay. They just sometimes use some different symbols. So instead of A in concentration, they will sometimes use N to represent nuclides going through decay, but it's basically the same thing. It's basically kind of the concentrations. In addition, again, they'll use N instead of A. In addition, is we oftentimes in sort of kinetics, like we talked about earlier, we oftentimes use sort of these guys as molarity and concentration. And the difference is here in nuclear decay, we oftentimes might not use molarity, very rarely. We could use grams and grams, for example. We could use something like milligrams and milligrams in there instead of molarity. We also could use a very common a rate. Sometimes we'll see something like CPM, which is counts per minute. So instead of sort of the concentrations, we sometimes will use rates, which is very common, and also things like grams and grams, milligrams and milligrams. So although we kind of think about sort of the kinetics equation there that you have to use molarity, you actually don't have to use molarity. You really just need to make sure that these units are the same, so that this guy and this guy are essentially the same. So if they're both grams, it will work. If they're both milligrams, it will work. It's all sort of the same. Another sort of difference that we sometimes will see in sort of nuclear kinetics, if you will, I don't really want to say it's different than regular kinetics because it's really the same stuff, is K. In regular kinetics, we call it the rate constant. In sort of nuclear chemistry, we call it the decay constant. And sometimes instead of K for that, people will actually sometimes use lambda as the decay constant. So that's another sort of symbol that we sometimes see. So we do basically do everything the exact same way. K again is our rate constant or decay constant. T is our time, remember, in that equation. And very much so, maybe more so than what we saw in regular kinetics problems, you oftentimes have to use both of these guys together. So a lot of times you will be given something where you might not have the decay constant. You might have to use the half-life to figure out the decay constant and then put it into sort of the integrated rate law. So these are very common sort of problems that occur using these guys, but ultimately it is the exact same calculations and stuff that we did in the kinetics chapter. Any questions on that? Obviously, half-life, like we talked about before, is the time it takes for half of whatever you started with basically to decay, right? So if you started with 20, after the first half-life, you'd be down to 10. After the second half-life, you'd be down to 5, down to 2.5, and so forth after each half-life. So these are also, should look familiar to you. These are the two first order graphs that we saw, right? And again, instead of A versus T, we have N versus T. Instead of natural log of A versus T, we have natural log of N versus T. And this is the one that we typically see, right? Because if we rearrange this equation here, natural log of N is equal to minus T plus the natural log of NO. This is our y is equal to mx plus b that we talked about. On the y is the natural log of A, or the nucleus, and on x is time here. The slope here will equal minus the decay constant, again, sometimes used as lambda, or minus k. I think your book might actually just use k, just like normal. And just like we saw before, we could take the slope there, and that would equal that. So these are the two same sort of equations that we've seen before. And again, a reminder, sometimes people in nuclear chemistry, because they like their own symbols, will sometimes use that lambda as the decay constant. And again, it's the same as K. So if you want to continue to use our regular first order kinetics equations, which I recommend because they're probably in your head, so you might as well just continue to sort of use it like we've seen it previously. That's probably a very good idea in this sense. So again, these two sort of formulas that we've seen before. Any questions on that? So here are some half-lives, and half-lives, as we just talked about, again, is the time it takes for half of whatever you started with to basically go away. And when we talk about radioactive sort of nucleuses, you know, some half-lives are years and years, some are, you know, days, some are hours, some are minutes, some are seconds. And there are different types of decay that happens, alpha, beta, you know, even gamma as well. So for example, if we look at uranium-238, which is popularly used in nuclear power plants and such, has a half-life of 4.5 times 10 to the 9 years. That is a lot of years for half of it to go away. None of us will be around, I don't think, for even one half-life of that deal. And, you know, so that's a very, very long time. This is carbon-14. This is something that we see a lot in sort of nuclear questions. Half-life is 5730. It's a beta emitter. And then we have some other guys here. You can have guys that you can see are very, very short. These, I mean, that's not even obviously 1 second. That's super, super fast. And, you know, usually about 10 half-lives or so, everybody is done in terms of what is left over at that point. So let's take a look at a problem here and kind of see. So why don't you give it a try and see what you come up with. If you have a 1.35 milligram sample of plutonium-236, calculate the mass that will remain after 5 years. Here's some information that might be helpful to you. Half-life is 2.86 years. So take a couple of minutes here and work it. Again, just like a regular kinetics problem, and see what you come up with. Okay, so let's take a look and see. So again, once you have anything to do with radioactive decay, always going to be your first order sort of kinetics. So you could always think about, again, you can use it just like we saw in the kinetics chapter, kind of the same way here. And again, our half-life, natural log of 2 over k. And we could actually just kind of count off what we got going. We have a 1.35 milligram sample. We want to know how much will remain after 5 years. So we do have T, which is the 5 years. We do have our initial given to us. We're looking for kind of how much is remaining. So we are still missing one piece of information here to allow us to solve for it, which is in this case the decay constant. And that is again where we can use our half-life equation to help us, because they did give us the half-life here of it at 2.86 years. So we're going to rearrange that and solve for k, because that will then allow us to solve for what we're really looking for. So in this case, k would equal the natural log of 2 divided by the half-life. That's going to give us the natural log of 2 divided by 2.86 years. That's going to get us something like 0.242 reciprocal years, right? So again, remember that is first order. Rate constant, decay constant is 1 over time, right? 1 over seconds, 1 over years, 1 over minutes is what we would expect in terms of the units. By doing that, we now have the decay constant, which is really the sort of last thing that's missing there. So we can then really plug into here our numbers. So again, the natural log of A, which is what we're looking for, is equal to the natural log of our initial, which is 1.35 milligrams. Again, we do not have to worry about it not being molarity. You could use it in milligrams. Minus the K that we just calculated, 0.242 reciprocal years, times our time, which was how much is left over after 5 years. Also a reminder that you need to make sure you watch the units between these two guys. In this particular case, we're good. We got years on both of them, so they do cancel. Just like in a regular kinetics problems, you may actually have different units of time. So you want to make sure you don't have different units happening here. Again, both of those units are going to cancel each other out. So if we do some cleaning up of the right-hand side here, we got, let's see here, the natural log of 1.35 minus 0.242 times 5, going to get us, looks like what we got going there. We got the natural log of A will equal minus 0.9099, we'll call it. And at this point, what we want to do is take the E of both sides, right? So we take the E of that side and we take the E of this guy over here. That's going to cancel that out. That's going to leave us just what our final is. So if I take the E of that, it looks like we end up with 0.403 units here would be milligrams to match our original units in this particular case. Any questions on that? So again, very similar to kinetics problems that we did before. Again, the nice thing about this is it's radioactive, so it's always going to be first order no matter what the difference is. Does this make sense? Well, it sort of makes sense because 1.35 milligrams, we ended up with something that is smaller. It is going through a decay process. So if for some reason you went the opposite way and ended up with more, that's not what should happen, right? So our final should always be less than our initial as it's going through a decay process. So it is moving sort of in the right direction there. Excuse me. And our answer does sort of make sense. And in addition, 5 years is just under 2 half-lives. So if you did 2 half-lives, you would be down to like 0.3 something. So this is 0.4. So again, does make sense. Any questions on that particular one? All right, why don't you try another one here as well? So radon 222 is a gas. Assuming no loss is if there's 10.24 grams in the house today, how much will be there in 5.4 weeks? Radon 222 has a half-life of 3.8 days. So take a couple minutes and see what you come up with. Okay, so on this one, same sort of approach here. We're going to use our kinetics equation. And in this particular case, we have 10.24 grams there today. Again, we can use grams, not a big issue. We want to know how much will be there after 5.4 weeks. And again, just like the previous one, we are missing the decay constant. So we are going to use the half-life here to help us figure that out. So again, the half-life being first order, going to be here, solving for our decay constant. Basically the half-life and the decay constant switch places, gives us a natural log of 2 divided by 3.8 days. That's going to give us something like 0.182, again, reciprocal days, 1 over days in this particular case. Now, as I was mentioning before, you do want to watch out units here. And in this particular case, we do have an issue. Our decay constant I left in days, but our time is in weeks. So again, we're going to get the wrong answer. We do need to do a conversion. You can either convert everybody to days, which is what I'm going to do here. Or alternative, you could converted this into weeks and did obviously weeks for everything. But they do need to be the same. Otherwise, again, you're going to run into an issue in terms of units. So I'm going to convert my weeks into days. So I believe in 1 week, there should only be 2 days, but we'll go with 7 days, I guess. There is 7 days, I suppose. So that's going to give us something like 37.8 days. So now I'm good in terms of units for both of these so that everything cancels. Now I'm good to go into my equation. Natural log of my initial, which was 10.24 grams, minus my decay constant, which is 0.182 reciprocal days. And now that I have my time into days as well, I'm all good in terms of units. So again, days are going to cancel. Going to really leave us with grams as the units that's going to be left over. So again, here, if we kind of do some cleaning up of the right-hand side, natural log of 10.24 minus 0.182. Maybe do some parentheses there as well. 0.182 times 37.8. Looks like we get the natural log of A is equal to minus 4.55 3298. Just like before, we're going to take the E of both sides here. And when we do that, that will get us a final amount that's there of, we'll call it 0.011. And again, here the units will be grams in this particular case. Also makes sense. Again, we started at 10.24 grams and we're left with basically nothing almost in terms of what's left over, 0.011 grams. So obviously did get smaller. Any questions on that calculation there? Again, pretty identical to what we did previous. Really, the major difference is the units. So we don't use molarity a lot in nuclear chemistry. We just use some different sort of units in there in place of it. But everything else works the same. All the calculations are the same as what we saw earlier. Any questions on that? Okay. In addition to doing some calculations like we been doing here, we could also do some radio dating of certain things by using really our same first order rate law, the natural log of A, natural log of A naught minus KT. The only difference is, for example, half-lives here. We could use something like if you're doing some carbon dating, you use the half-life of carbon, which is what this is, and that's the 5730 in for our half-life. We could do some uranium dating as well. Again, half-life here, as you can see, a little bit longer at 4.51 times 10 to the minus 9. So sometimes they'll use radio dating here with our uranium here. They'll measure how much lead was produced and really sort of products minus reactants. You can figure out how much uranium was still left over at that point sometimes. Again, really, these work the same way. They're really just kinetics problems. The only difference is in these type of problems, because it's something to do with sort of dating of something, how old something is. Most of the time when you use your first order rate law, you oftentimes will be solving for time. So usually you'll be solving for time in this case, and that's sort of the only sort of difference between them. So let's take a look at one here. An ancient skull gives 4.5. That's disintegrations per minute per gram of carbon. That's what that means. This is disintegrations per minute per gram of carbon here, not Celsius. So that gram of carbon that we see here is really important because that tells us kind of the half-life that we can use. In this particular problem, it would be the half-life for carbon, which is 5730 that we just saw there. A living organism gives 15.3 disintegrations per minute per gram of carbon. How old is the skull? So we want to do this by using our rate law, or not rate law, our first order rate law, I guess it is, and figure out basically how much time is left. So this works the same way. We're just going to use these guys here instead of, say, molarity. So these are rates of radioactive decay. So we could use that inserted into our rate law just like we would. So the important part here is carbon. So carbon tells us that the half-life that we're going to use is our 5730 years. So if we just look at our kinetics rate law here, we have a ancient skull. So that's kind of like dead, it's over, it's final, right? So that is our A. Living is like how you start, right? So that is our initial. So we do have both of these numbers. We are looking for time, how old it is. So just like what we saw before, we will need to use the half-life equation here to figure out our decay constant. And that's again why these grams of C is important, because it is grams of carbon, which tells us we want to use the half-life here for carbon. So doing that, again, our half-life equaling natural log of 2 over K. K is equal to natural log of 2 over our half-life. That's going to be the natural log of 2 over 5730 years. That's going to give us a decay constant of 3 zeros, looks like. So 1, 2, 3 zeros, 121. again, reciprocal years as our decay constant. We now have our decay constant, so we can plug in our numbers. Again, natural log of our old, which is our final, so that's 4.5, equals the natural log of our living, which is beginning, our initial, minus our decay constant we just got. And again, here we are solving for time. So what we want to do is basically take the natural log of 4.5. We're then going to subtract the natural log of 15.3. That's going to give us minus 1.223775 is equal to minus 0.000121 reciprocal years. We want to divide that 0.000121 to the other side, not just that number, but also the negative sign that goes with it. And that is going to give us a time that is equal to 10113 years. Maybe doing some cleaning up of it. 10100 years. So it looks like our skull is about 10,000 years old based on the information here. So that does make sense. We would expect it to be probably old. Any questions on any part of that calculation? Again, very similar to what we've been doing and what we've done before. Since we're doing some type of dating here, we are just really looking for time. And as you can see here, we didn't have grams or milligrams, we didn't have molarity, but we're able to use some type of version of radioactive decay, our rate of radioactive decay in our equation as well. Any questions on that? All right, why don't you give one a go then and see what you come up with. Why don't you do this one here? So we found a rice grain dating back to 15,600 years ago. If a living sample gives 20 counts per minute per gram of carbon, what would be the number of counts per minute per gram of carbon of a rice that's found on the site? So again, we're dealing with grams of carbon, counts per minute. It's another rate of radioactive decay. So again, just to give you a hint, you should probably use the same half-life, 5730 years. All right, take a couple minutes and see what you come up with. What is the counts per minute of our piece of rice that we found on the site? Rate law here. So again, this is a rate. So this is counts per minute per gram of carbon. And what would the number of counts per minute per gram of carbon be on one that was found there? So a living sample is our initial. So that is what that is. Kind of the dead or oldest sample would be our final, kind of like life, right? You live and then you die. So anything living is sort of initial, anything sort of old, ancient is sort of the ending part there. The time here was, it was dated 15,600 years. So we do have time. So again, super common in these problems. We're again missing our decay constant here. So in this particular case, we would use our half-life and our formula that we saw. And because it's really the same number as what we just did in the previous problem, we will end up with the exact same decay constant, which is 0.000121 reciprocal years. At that point, we're good to go in terms of plugging and chugging into here. So our final counts per minute would be our initial, which is 20, minus our same decay constant as previously. And again, in this case, in terms of units, we are okay because they are both in years, so they do cancel. So if they were not both the same units, much like we talked about previously, you would want to make sure that you get them to the same units. And again, it really doesn't matter which unit you kind of choose there, as long as they are both the same. Looks like we end up with then the natural log of A, and if we clean up the right-hand side, 1.108 and 13, we'll call it. We're going to do an E on both sides like we've been doing, and that will get us, looks like 3.03. The units here would be counts per minute per gram of carbon. So they would be the same units as the other guy in terms of the final. Again, also does make sense. We started at 20, it's decaying, so we would expect something that's been around for 15,600 years, probably has gone through some half-lives and probably has not given off as much radioactivity as obviously a fresh, new, living one. Any questions on that problem or kinetics associated with radioactive decay? Again, the good news is we've done these problems before. Also, good news is you don't even have to sort of think about is it first, second, or zero order. It's always going to be first order here when you're dealing with radioactive decay. Any questions on any of that there? Okay, so the next thing we're going to talk about then is sort of the energy associated with sort of nuclear reactions and sort of fission type reactions to specifically talk about. So when we talk about sort of fission reactions, I remember we saw a little bit earlier spontaneous fission. Whoops. But you can also sort of make a fission reaction occur. But the ultimate sort of parts of a fission reaction is you have this sort of unstable nucleus that develops, and it essentially will split off into two new nucleuses. Usually will give off some neutrons along the way, 1, 2, 3 neutrons, a lot of times few different neutrons. And most importantly, it will also give off some energy along the way. And during this process of nuclear fission, some of the mass of the nucleus is converted into energy. So as we'll talk about in just a second, there's a difference in the mass if you add up the mass of all the nucleons, which is your protons and neutrons, those particles that are found in the nucleus. If you add up the mass of those guys and the mass of the actual isotope or nucleus itself, there's a slight difference in mass. And as we'll see in just a second, that difference in mass is what's referred to sometimes as the mass defect. And that mass defect is sort of converted into energy via this guy's equation right here, E equals mc squared. That I believe is Einstein's equation. M is mass, right? And c is the speed of light, which is 3 times 10 to the 8 meters per second. So using sort of Einstein's equation is one way that we could calculate this, and we can figure out the energy that's associated with that slight difference between sort of all the individual particles that make up this isotope and the actual mass of the isotope. So there's a slight energy difference that gets sort of converted into mass difference that gets converted into energy. Now, each mole of uranium-235, which is a common sort of starting fuel for nuclear reactions, like in, say, power plants and stuff like that, produces about 1.7 times 10 to the 13 joules of energy. If you compare that to a very exothermic chemical reaction, where exothermic means energy and heat is being given off, it produces somewhere on the order of 10 to the 6 joules per mole. So you can see that's almost at least 10 to the 6 to 10 to the 13. That's an incredible amount of difference in terms of the energy that's produced in a nuclear reaction versus your most sort of exothermic hot sort of reaction, chemical reaction that takes place. So that's why a lot of times they have in past and so forth, as we'll talk about, use sort of nuclear reactions for nuclear power plants. It generates a lot of heat, which is really good in those situations to provide energy. We'll talk about how that actually works in just a bit here, actually. So as I was mentioning, that difference in mass between sort of the protons and neutrons that are there, and the mass of the actual nucleus as well. The slight difference is what is known as the mass defect, which is what this says here, mass defect. Again, nucleons is basically your protons plus your neutrons. And when we look at Einstein's equation of E equals mc squared, the m here can be used as the mass defect in this sort of calculation. So there are sort of a couple of different ways you can approach these type of problems. They're both really based off of Einstein's equation E equals mc squared, except that in certain cases, you know, they sort of have conversions that you could use instead of sort of doing E equals mc squared, but it's really based off of it. The energy released when a nucleus forms is called the binding energy. And I don't know if you can see it or not on my screen. It's really light. That's binding energy. And some important conversions that are sometimes helpful here are these two guys here. 1 mega electron volt, which is what that MeV stands for, is equal to 1.602 times 10 to the minus 13 joules. Also, one AMU, a mass defect, is equal to 931.5 mega electron volts. Some other important sort of conversions that's important to remember is, hopefully you remember, a joule is equal to a kilogram meter squared second squared. So a kilogram times a meter squared over a second squared is what a joule equals. So that's also an important sort of conversion. And using sort of Avogadro's number as well is sort of an important conversion. And we'll talk about doing that in just a second here. But what we have is something like Avogadro's number, but it is actually 6.022 times 10 to the 26 AMU in a kilogram. So looks very much like Avogadro's number, but Avogadro's number is to the 23rd, and that's per grams. This is kilograms, so that's why we're to the 26. So this is sort of that relationship that's also helpful as well. So in certain cases, you may be asked, you know, what is the binding energy or the nuclear binding energy in mega electron volts, or you may be asked for it in joules. And there's really a couple of different ways that you can sort of do that. Now, let's take a look at an example of one and kind of work it both ways, so you can kind of see, you know, how you get to, you know, the same answers, and it's up to you sort of which way you want to kind of do it. So let's take a look at actually and try to calculate the nuclear binding energy, which again is the energy required to break up a nucleus into its basically protons and neutrons. And let's take a look at really fluorine 19. And fluorine 19 has an atomic mass of 18.9984 AMU. Okay. So if we wanted to calculate this, one approach, and actually in both cases you need to do this, we need to figure out the mass defect. So the first couple of things that we want to figure out is how many protons there are. So there's definitely 9 protons, and that comes from the atomic number. There are 10 neutrons, which comes from the mass number minus the atomic number, which in this case is 19 minus 9, gives us 10. So to calculate the mass defect, we take the mass of 9 protons in this case. So we take 9 times 1.0078 0.25 AMU, and that is the mass of a proton. We're going to add it to 10 times the mass of a neutron, which would also be provided to you, 1.008665 AMU. And this is basically the mass of all the components that make up the nucleus. There's 9 protons in there. There's 10 neutrons in there. They each have a certain mass associated with it. And we're going to subtract it from the actual mass of this isotope, which is 18.9984 AMU. And if we do that, we will end up with 9 times 1.00782 plus 10 times 1.008665. And we're going to subtract it from the mass of the isotope, which is 18.9984. And it looks like we end up with 0.158, well, we'll call it 6, 0.1586 AMU. That 0.1586 AMU is what is referred to as the mass defect. That is the difference in mass of the actual subatomic particles, the protons and neutrons that make up the nucleus, and the actual mass of the isotope itself. So that slight difference is what is going to get converted into energy. And again, we could calculate this one of 2 ways. We can use Einstein's equation. So let's do it that way first. So using Einstein's equation, E is equal to mc squared. This would be m in this case. So that would be 0.1586 AMU times our speed of light, which is a constant. And that will give us times 3 to the 8 squared. Looks like something like 1.43 times 10 to the 16. The units that we are in right now are AMU, meter squared, second squared. And that is close to a joule, but it is not a joule. So we do need to do a conversion of 1.43 times 10 to the 16 AMU meter squared second squared. This is where we use our Avogadro-like number here, which is 6.022 times 10 to the 26 AMU per kilogram. And if we do that, we will get 2.37 times 10 to the minus 11. The units at this point will now be kilograms, meter squared, second squared, and that is the same as a joule. Any questions on that up to that point? Now, very commonly, when we talk about nuclear binding energy is given in joules per nucleon or mega electron volts per nucleon. So very common, we would take this number and divide it by our nucleons, which is 19 in this case, basically our mass number. And we will end up with, looks like 1.25 times 10 to the minus 12 joules per nucleon as the binding energy here in joules per nucleon for our fluorine 19. Any questions on that? Now, we can also, if we want, convert this into mega electron volts per nucleon. And we could do that by dividing this number by that conversion that we just saw, which was 1 mega electron volt is 1.602 times 10 to the minus 12, I believe, minus 13 joules. And if we do that, we get 1.602 to the minus 13. We get something like 7.79 mega electron volts per nucleon. So using Einstein's equation, we could get joules per nucleon and mega electron volts per nucleon using this conversion that we saw on the previous page. And those are two very common units of nuclear binding energy. And we could actually use nuclear binding energy to determine stability. So the higher the nuclear binding energy is per nucleon, the more stable something is. Now, I said there's a different way that you could do this problem, and there is, and you will end up with the same answers. So this is sort of using Einstein's equation. Any questions on that part of it? Now, if you didn't want to kind of use Einstein's equation and you kind of wanted to maybe just use those conversion factors that we saw here, that's in the box, you can actually use the conversion factors in the box there and go really right from the mass defect to really figuring out, the binding energy relatively quickly without technically using Einstein's equation, even though you kind of are anyways. But if we were to do it the alternative way, where we're going to use those two conversions, and one of them is 1 AMU is 931.5 mega electron volts. The other one is what we just saw there, that 1 mega electron volt, 1.602 times 10 to the minus 13 joules. We could pick up the calculation from the mass defect, which was 0.158. Did we do 6? I think we did 6 on that one, right? What did we do there? 6. Yep. 6 AMU. And we could go directly from AMU into mega electron volts by using that conversion. 1 AMU is 931.5 mega electron volts. And that will get us 0.1586 times 931.5. Gives us 147.7 mega electron volts, which if we at this point divide it by 19 nucleons, we end up with our 7.76 mega electron volts per nucleon. And that should hopefully be the same as we got over there, 7.79. So pretty close with rounding. This would be 7.78 if I rounded pretty close to what we had before. So we'll just round kind of similar to what we had. 7.78 nucleons, mega electron volts per nucleon. And then if we wanted to, we could just take this number and use our other conversion. And we could convert it into joules if we wanted joules as well. And we obviously should get, with rounding, pretty close to what we had previously, 1.25 times 10 to the minus 12 joules per nucleon, which hopefully should be about what we had on the other side. So again, with rounding, you should come up pretty close. So this is an alternative way that you could do these problems, more of the sort of conversion factor approach. It really is based off of Einstein's equation. You could do Einstein's equation, and you can see you get pretty much the same sort of answer. Any questions on either way of those, doing those calculations? Those conversions probably will be provided for you. So a lot of times people will kind of choose to sort of do it in that fashion. Any questions? But again, you could plug it into Einstein's equation and obviously get the same way. So as I was mentioning earlier, we can use nuclear binding energy per nucleon as a measure of stability. And again, sort of the higher the nuclear binding energy per nucleon is, the more stable something is. So as you can see here, really we max out in terms of stability right here as an isotope of iron, iron 56, sort of the highest in terms of stability. So this is another way that you can sort of compare the stability of certain isotopes. If you have the nuclear binding energy per nucleon, you could put them in order based on highest is the most stable, lowest is obviously less stable than the others. Here's just another graph where we again see sort of the same thing. Most stable nuclides happen, in this range here. And as a result of fission or fusion, as we kind of push to get things to stable nuclei. So again, things will go through here through fission or fusion and making those guys more stable. Fission, again, is that kind of separation of everybody into two new nucleuses and some neutrons and some energy. Fusion, as we'll talk about towards the end here, is sort of putting together two smaller nuclides to form a larger one. That usually occurs at very, very high sort of temperatures where that does happen. All right, so why don't you give one a go here and see what you got. And there's the mass of a proton and mass of a neutron that you could use. Let's calculate the mass defect and nuclear binding energy per nucleon in mega electron volts. Why don't we do both just to make sure? So why don't we do it in mega electron volts per nucleon and joules per nucleon. So take a couple of minutes, see what you come up with. Let's do it in both. That way we make sure, and then we'll talk about it. Of 16.014701. We're going to basically figure out what is going on in terms of protons and neutrons. So we could go to the periodic table. We see the atomic number is 6. So that obviously tells us we do have 6 protons. If we take our neutrons, which would be 16 minus 6, that gives us 10 neutrons in this particular case. We're going to use that to help us calculate the mass defect. So the mass defect here going to be the mass of our 6 protons, each one being 1.00783, plus the mass of our 10 neutrons, each at 1.00866. And we're going to subtract that from the mass of the isotope. Remember, there is going to be a slight difference in the mass of these guys. And that's what's going to be sort of converted into energy. And it looks like it is 1.00783 plus 10 times 1.00866 minus a 16.014701. That's a lot of numbers. We end up with a mass defect of, we'll just call it 0.1189 AMU. Any questions up to there? Now, as we sort of talked about just a second ago, you really do have 2 options. You could go into Einstein's equation, and if you go that way, you will end up with the joules answer first, or you could use the conversions if you like and get to the mega electron volts. So I'm just going to do sort of the conversion factor way, which would be not that. Missed the 1 there. Try that again. Take 2. All right, so 0.1189 AMU. And since I am interested in mega electron volts, I can just use that conversion factor that an AMU is 931.5 mega electron volts. That's going to get me, looks like about 110.7 mega electron volts. I do want to divide it by nucleon. Nucleons, the protons and neutrons, which is 16 basically. So we're going to divide this by 16 nucleons. And that will get us, looks like 6.9 921 mega electron volts per nucleon, as what the original question asked for. Any questions up to there? And since we were also interested in joules per nucleon, we could also use that conversion factor to convert this guy out of mega electron volts. Again, our mega electron volt is 1.602 times 10 to the minus 13 joules. So 1.602 to the minus 13 looks like something like 1.11 times 10 to the minus 12 joules per nucleon. Any questions on either one of those there? Okay. All right, why don't you try one more just to make sure? So let's see what we got here. So calculate the binding energy per nucleon. Let's do mega electron volts per nucleon on this one. And the mass of iron 56 is 55.93494. And again, a reminder that our protons has a mass of 1.00783. And our neutrons has a mass of 1.00866 AMU. All right, take a couple minutes, see what you come up with. And we're going to use that to figure out our mass defect. So mass defect here going to be our 26 protons times the mass of a proton plus our 30 neutrons times the mass of a neutron. Again, basically the components that make it up. And we're going to subtract that from the mass of the actual isotope itself. That is going to give us that mass difference between really the particles that make it up and the actual mass of the isotope itself. So it looks like 26 1.00783 plus 30 times 1.00866. And I'm going to do a little subtracting, 55,93494. Going to get us a mass defect of 5284, looks like. And again, you do have both options. You could use Einstein's equation. You could use those conversions. So since we went with just mega electron volts, I am going to just use the conversion way of doing it. So that would get us 0.5284 AMU. Again, using that in an AMU, there's 931.5 mega electron volts. That gives us 492.2 mega electron volts. Remember, we typically give this per nucleon. So 56 is really our protons and neutrons, and that's what a nucleon is, what's in the nucleus. So basically your mass number divided by 56 gets us 8.790 mega electron volts per nucleon. First off, any questions on that particular one? Okay, so this is again how you can calculate nuclear binding energy per nucleon. Again, it is a measure of stability. So if we look back on the sort of the three that we just did and sort of the binding energy per nucleon, and we'll just look at a mega electron volts since we have that number for each of them. We started out with fluorine 19, which ended up with something like 7.78 mega electron volts per nucleon. We did carbon 16 just a second ago, which ended up with 6.921 mega electron volts per nucleon. And then obviously we have the one we just did here, which was our iron 56, which was 8.790 mega electron volts per nucleon. So the higher the binding energy per nucleon, the more stable. And as we saw in that graph, if you remember, way up on top of that graph was iron 56, which is the most stable there. Then you would go with obviously fluorine 19 next, and carbon 16 would have a lower nuclear binding energy per nucleon, which would make it perhaps less stable. So again, you could also use these values as a measure of stability. Larger the value, the more stable it is. Any questions on that? Okay. So the next thing we're going to talk about is nuclear transmutation. So, you can have spontaneous fission, but a lot of times we can sort of make sort of man-made elements or kick off sort of a fission reaction through transmutation. And that's basically what we see here. We shot like an alpha particle at each of these, a proton at this guy. One way that we could do that is using a particle accelerator. It's got sort of an electrical field, magnetic field, and basically you get the particle sort of spinning really fast, and then you sort of shoot it right at the target. Obviously, the target nucleus is not going to be very happy per se when that particle comes in. It's going to probably separate and go through perhaps fission, make some new nucleuses as well, or even make some new elements. And that's how we get a lot of those sort of man-made elements that you see sort of at the bottom of the periodic table and stuff like that. Things like californium, berkelium, einsteinium, all these sort of things. As you can see, each of them, a lot of them do start with some type of particle that gets sort of shot at something, causing it to become unstable and really form a new element in that sort of case, or a new nucleus in that particular case. We could also use sort of this process in a fission reaction. So in a fission reaction, we could actually start it off as we see in this sort of picture here. We have sort of a stable nucleus, uranium nucleus here, uranium-235 looks like. We shoot like a neutron at it. It becomes very unstable, like a bowling pin here. And it ends up splitting off through fission into two new nucleuses. Also gives off a number of neutrons in the process, and also a lot of energy is sort of released as well. So if you just sort of do a quick calculation here, products minus reactants, the difference here that you have, we get something like 2.0 times 10 to the 13 joules for every mole uranium-235. And if you take a ton of coal, which if you're not familiar with, we'll talk about here in just a second as well, the two major sort of sources of energy in our sort of society or country here, for the most part, for a lot of years, was either basically burning coal to basically produce energy, or using basically uranium in sort of a nuclear fission reaction to help produce energy. And we'll talk about how that occurs in just a second. But you can see there's a major difference in terms of the energy output that you get in, say, a fission reaction versus, say, that exothermic combustion reaction. We'll also talk about it as well, that, the production of these neutrons can be also problematic, because as you can see here, what sort of starts the reaction is a neutron. You're actually producing neutrons as well, which then could theoretically go back and sort of start the whole reaction over again. And as we'll see, that's sort of what is referred to as a chain reaction, where it's just sort of self-feeding sort of reaction that can occur. Now, you don't always get perhaps the same two elements or new nucleuses that are formed in a fission reaction. So you won't always get, in this case, strontium and, say, xenon. You will usually get some neutrons, and you definitely will get energy. But what we see here is sort of common mass numbers that are produced as a result of fission. And again, guys with mass numbers in this range, guys with mass numbers in this range are commonly what you sort of get as a result of these guys going through this fission reaction. Again, you don't always get the exact same two guys every time. Sort of randomish a little bit. So this fission reaction can be good, can be not so good in certain situations. So as I was just mentioning before, sort of what can kick off this reaction is sort of a neutron basically hitting a uranium nucleus, causing it to become unstable and start to split. The problem, though, is because it does produce neutrons as a result of that reaction, like I mentioned a minute ago, those neutrons could then really come back around and sort of start the whole reaction again. And you can get a reaction that's sort of self-sustaining and grows sort of exponentially every time that sort of occurs. So remember, every time this occurs, it is making new sort of radioactive nucleuses, but most importantly as well, it's producing a lot of energy in every sort of step along the way. So you can see if it continues to build, you're building a lot of energy that will happen. And that's what's sometimes referred to as a nuclear chain reaction. And that's sort of a self-sustaining sequence of nuclear fission reactions. So what is needed for that to happen is you need what is sometimes referred to as the critical mass. And you need to start with a critical mass of, say, something like uranium to keep this fission reaction going. If you don't start with a critical mass of it, it will kind of fade out basically, or be sort of under control. If you have a critical mass, it will just keep going, going, and going, obviously producing a lot of energy, B, a lot of radioactive products along the way that's going to be there for a lot of years along the way. That's essentially how sort of a nuclear sort of bomb works, if you will. They have sort of a subcritical mass of uranium separated, but obviously once it hits, that allows both of these guys to come together, and you basically make a critical mass of something like uranium. And obviously with the dynamite that's in there, that's going to cause enough energy to kick this reaction off, and it will continue to basically grow exponentially, giving off energy and stuff like that, which is obviously not such a great thing. Right? But we do use this fission reaction in things like, say, nuclear power plants, for whichever ones are still in operation. And this is sort of a nuclear power plant sort of schematic. We'll talk about some of the different parts of it, but in general, up to, recent times, the majority of our energy came from, one of two major sort of sources. Obviously, we're getting other things like wind and stuff like that now, but they either come from sort of a nuclear power plant or sort of a traditional coal power plant. And really the only difference in it is sort of what they use, either sort of a fission reaction or a coal reaction. Because really when we go and how a power plant in general sort of works is essentially there's water, and essentially we heat the water. When we heat the water, obviously we make steam. The steam can then go out to turbines, to generators, and then you get lights, right? When you throw the light switch, all that good stuff. Nice thing about that is obviously you can cool down the steam and kind of recycle it, right? And go through condensation and do this process. So the major difference between, say, a traditional power plant and a nuclear power plant is basically how they heat the water. In a traditional power plant, they basically burn coal, and they use the heat that's coming off of the coal basically to heat up the water. In a nuclear power plant, they do a fission reaction, and they use the energy coming off of that fission reaction basically to heat the water as well. And that's what we see here. So this is sort of a schematic of a nuclear reactor. You probably have seen some around us, San Onofre, the two big domes that you see off the 5 freeway, right? That's sort of the nuclear power plant right there by some water and all that good stuff. But kind of works the same way. They have sort of a compartment where, all the radioactive sort of part occurs. And inside here, we have what are referred to as fuel rods. Fuel rods are almost like little erasers of like uranium. And they basically kick off this fission reaction in here. And obviously when they do so, there's also some, liquid in here as well. The heat from this reaction is basically channeled through another tank of water. And obviously, the heat from there is going to cause the steam to occur. The steam will go out to the turbines and all that good stuff and be used for electricity. We then can cool down that steam and get back the water and sort of do this recycling process that occurs. We also, a lot of times, will need to cool it down. So that's usually why nuclear power plants are by big bodies of water, like ours is right there on the ocean, right? Good surfing over there in San Onofre, but big water over there in the ocean used to sort of cool everything down. Out in Arizona off the 10 freeway, they have a nuclear power plant. And if they don't have sort of a big source of water, a lot of times they'll be a big kind of cooling towers of big things of water basically to use to sort of do that recycling program. So you may be asking yourself, why does this not go out of control, and why does it not perhaps continue on in a chain reaction? And there's a couple of sort of safety measures that they obviously usually keep in a nuclear power plant. One such safety measure is they keep the mass below critical mass. So they keep the amount of uranium below that critical mass, which means, if it did kind of go, it shouldn't be able to sort of self-generate and continue to basically continue on and that chain reaction happening. The other important thing that they have in there is they have what are referred to as control rods. These are kind of the greenish guys, I think, in this picture. These control rods, they basically are soaked in things like perhaps cadmium or something like that. And basically what they do is they absorb neutrons. So why is that important that they have these control rods that absorb neutrons? If you remember basically how this reaction starts, it starts with a neutron, right? Hitting a uranium. So by having these control rods in, what they're able to do is sort of pluck out a lot of these neutrons that are generated as a result of this reaction, and they're able to sort of maintain the reaction in sort of a controllable sort of fashion so that it doesn't go out of control and become sort of a chain reaction. So those are two really important sort of control points that they have in a nuclear power plant. They have these control rods which sort of grab out the neutrons in this sort of fission reaction, keeping the reaction under control. And they also keep, obviously, the amount of uranium there under critical mass. Any questions on that? Now, there's good and bad, I guess, in terms of both types of power plants. Obviously, coal-fired plants give off a lot of pollutants like sulfur dioxide, carbon dioxide, and those type of carbon pollutants and sulfur pollutants. In terms of nuclear power plants, they give off a lot of stuff that is obviously very radioactive, right? So you have a lot of radioactive waste that has half-lives of years and years and years. Like some of the stuff has half-lives, like I said earlier, that none of us will be able to live to see even one half-life. So you have a lot of issues as to where you store it, where you keep it, what do you put it in, who watches over it for all those years, and keep track of that sort of nuclear waste. So, there's good and bad for both of them. And that's some of the issues. For a lot of years, a lot of these nuclear power plants would keep sort of all that stuff on site because nobody wanted it sort of shipped through their towns and stuff. I think in Nevada, they built the big hole in the ground where they kind of started, I think they've started using it in the last several years or so, sort of keeping all that type of stuff over there in that area. And this is also some of the hazards of these fission reactions is you get a lot of what's sometimes referred to as spent fuel. And spent fuel are really the products of these fission reactions. So for example, if you do some type of nuclear reaction for say a power plant, you get a lot of this spent fuel, which again is that stuff that you kind of have to store for a long period of time. And this stuff in terms of years, as you can see, has very big half-lives or times, and you have to store for years, talking about hundreds and hundreds and maybe even thousands of years before this stuff is not so active and stuff like that. So again, that brings up a lot of issues in terms of how do you keep it, where do you keep it, who's sort of responsible for it. Another type of reaction, which is a fusion reaction, which is sort of different than a fission reaction. In a fusion reaction, we take two small nucleuses and we basically combine them together to make one nucleus. And this happens at very high temperatures. Like you're going to take a vacation on the sun type temperature. That's how hot we're talking. So here we see a couple of hydrogens coming together to make one. Again, two guys making one here, which is a fusion. So fission, we have the separation of an unstable nucleus into two new nucleuses. Neutrons are formed, energy is given off. And fusion, we're taking two small things, making a larger one, again, occurring at very high temperatures. Any questions on that there? All right. And to sort of finish up talking about sort of nuclear chemistry here, obviously nuclear chemistry or radioactive isotopes are also used in medicine. So we do use it in medicine a lot, and can be used for treatment. You know, they still do, I think, and they used to years ago very commonly would put sort of radioactive seeds, say in tumors and stuff like that, to try to shrink them. We also do use a lot of radioactivity to do sort of scans and imaging. The nice thing about a radioactive isotope and say the regular isotope or the regular element is that they will behave pretty much the same way, say in your body. So, you know, if you put something in there that's radioactive, the benefit of it is you could kind of follow the radioactivity and sort of see where it is, what's happening with it. You could also use it as imaging, as you can see in sort of this picture as well. These are brain images with iodine 123. Again, it's able to sort of get into those areas just like normal elements would in your body and sort of highlight it and sort of scans and stuff like that. Obviously, giving people better imagings of stuff and seeing what's happening, perhaps, you know, in terms of disease and stuff like that. As well as you can see here, here's a bone scan, again, with technetium-99. And again, sometimes things will last in terms of their half-life. When we think about using radioisotopes in medicine, we clearly would want very small half-life, right? So we wouldn't want to give somebody obviously something that has a very long half-life. Otherwise, the follow-up appointment would be a lot of years down the road, right? So we want something that has a very small half-life. So sometimes they use things with hours, minutes, maybe seconds, sometimes days. But, you know, obviously, you probably wouldn't be treating somebody with something that has a half-life of many, many, many years, because obviously that would be something that's very, very radioactive for a long period of time. So usually when we do anything with medicine and sort of radioisotopes, it is usually something with very small sort of half-lives. Another important tool in sort of when you work with something that's radioactive or radioactivity, a lot of times you will use something like this. This is a Geiger counter. Geiger counter basically has a wand that basically does a reaction in terms of voltage here in this window, picking up on some radioactive measurements. And it gives off a signal and usually some type of audible sort of sound, like click, 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 click type of sound. You kind of go it around. The more clicks you hear, the probably more radioactive you're pointing it out. So a lot of times in laboratories, if you do research with radioactivity, which is very common, and part of the cleaning up process, part of doing sort of the research as well, you oftentimes will use a Geiger counter going around the lab just to make sure, you know, you didn't sort of make the entire lab radioactive and stuff like that. And definitely after you clean it up, you want to go back through and make sure, you know, it's safe to use without any more precautions and stuff like that. So a Geiger counter is a pretty important sort of tool that's used. Also, if you do a lot of research with radioactive materials, they oftentimes will give you like a ring, like a little badge that you wear, and every so often they sort of develop it and sort of see how much radioactivity you've been exposed to. It used to be film years ago. They developed the film and see how much exposure there was on it, and tell you should probably stay out of the lab for a while if you had a lot of exposure. If you didn't have very much, you know, you can continue on. If I took a Geiger counter and I just kind of held it up in the air, would it go off? And the answer is yes. Hopefully it shouldn't go off super loud, but it will click and stuff like that. There is background radiation. So there is background radiation around us at all the times. And there's a couple of sort of units of radiation that we sometimes talk about in terms of biological effects. One is a rad, which is a radiation absorbed dose. And that's sort of the conversion. That's how you do it. 1 times 10 to the minus 5 joules per gram of the material. There's also a REM, which is sort of the equivalent for men. And it is based on sort of the type of emission that it is. So X-rays, I'm sorry, gamma rays has a factor of 1, beta has a factor of 1. Remember, those are sort of our 2 most sort of penetrating radioactive particles. Alpha particles don't penetrate as far. But we do, as you can see from this sort of chart here, pick up some, radiation. This is a little bit older of a chart. I don't remember what year this was from, but we do get it from different sort of sources, ground and surroundings, air travel, how many X-rays and stuff like that. You sort of take. If you happen to live near, I guess, weapons testing or a fallout sort of center, or nuclear waste as well. If you live in there or something like that, obviously you get some exposure sort of every day. Again, only becomes sort of a problem if you have, obviously, in terms of exposure, if you're ever working with radioactivity or radioactive sort of isotopes, it's always important to find out for yourself, because unfortunately sometimes people don't always tell you everything about it. You should always want to make sure what type of emitter it is. You always obviously want to minimize your exposure to it in terms of time. And obviously you want to wear any type of proper protective equipment. Again, that could be as simple as gloves and a lab coat, to gloves, lab coat, lead, shields, and all that kind of stuff that's needed depending on sort of what you're using. So really, really important, especially if you're using any type of radioactive material, to always know what it is, know what type of emitter, and know the proper sort of protective equipment that you need to use. And as you can see, since alpha doesn't penetrate as far, you could get a little bit more exposure to alpha sort of guys that give off as a factor of 20 versus, again, or kind of more penetrating gamma and beta rays. Any questions on that there? Okay, that is it in terms of chapter 21. So what we have left, as I talked about earlier, is we have chapter 20, which is organic. So we will do that on Thursday. We will also do the lab, I think, that goes with it sort of on Thursday as well. And like I said, that will actually wrap it up, I think, for the semester here. And then we have finals next week, if I'm not mistaken, again, Tuesday and Thursday. I'll double check those times and all that, and we'll talk about it on Thursday as well. I think all you got left right now is a lab report that's due today that I think is the galvanic cell one, if I'm not mistaken. So make sure that you do get that in. Other than that, if you are good, I am good for today. Thank you for listening to the double lecture here. And we will pick back up on Thursday, our last day. And any questions on any of that stuff?